I'm Dr. Devidas Gulwade from Department of Physics, Vivekanand Education Society's College of Arts, Science and Commerce. This presentation is about a Excel utility which is useful to understand the conclusions drawn by Kronig and Penney model. But before we discuss about it, let us quickly review this topic. First, free electron theory was proposed by Drude in 1900. Prior to that, electrons were discovered, but the structure of atom and periodic arrangement of atom was not established. Drude proposed two postulates. One is called as a free electron approximation, which means electron do not interact with ion core, is essentially independent of that. It is completely free. It can roam freely inside the lattice. Second is independent electron approximation. That means electron do not interact with each other. And kinetic theory of gases he used to develop a model. This theory was partly successful but had few drawbacks. To overcome these drawbacks, Sommerfeld came up with his theory, which makes use of essentially the same postulates. Free electron approximation is used here, with the modification that the quantum statistics, Fermi-Dirac statistics, is used. Both of these theories had certain drawbacks. To name a few is overestimation of electronic specific heat, and it could not explain the positive coefficient of Hall effect. Also, importantly, it cannot differentiate between the metals, semiconductors, and insulator. So, to overcome these drawbacks, a new theory is proposed by Kronig and Penney, who says that electrons are not free inside the lattice, rather, they are in a field, in a potential created by the atoms. And approximation here is that the potential is in the lattice is periodic and it is a rectangular potential as shown in this diagram, which has a periodicity of A plus B, which consists of two regions. Region from 0 to A has the potential energy 0, and region from minus B to 0 potential energy is V0. So essentially, to analyze it further, one would start with Schrodinger time independent equations for two regions 0 to A and minus B to 0, which are written below that potential. And after using the boundary conditions and all that rigorous calculations, it established the equation, that is P sine alpha A upon alpha A plus cos alpha A is equal to cos Ka, which is called as Kronig and Penney equation, which means that solution exists only if this particular condition is satisfied. In this equation, alpha is under root of 2me upon h cross square, and P, which is also called as strength of a potential barrier, that formula is written over here. Essentially, it consists of height and the width of the potential barrier. Now, let us look at what conclusions are drawn from this particular equation. To understand it quickly, let us consider the two extreme. Let us say that P is tending to infinity, very high. Now look at the equation. P sine alpha A upon alpha A plus cos alpha A is equal to cos Ka. Means right hand side is a cosine. That means left hand side also, or only those values of alpha A are acceptable for which the value of left hand side is between +1 and -1. Now, if P is tending to infinity and you want the value of left hand side to be plus minus within +1 and -1, that means sine alpha A upon alpha A should be tending to 0. Let us take an extreme that let sine alpha A is equal to 0. That means alpha A is equal to n pi, or alpha is equal to n pi by A. If we square it, is alpha square is equal to n square pi square upon A square. Now, just now, while discussing the Schrodinger equation, we said that alpha square is equal to 2me upon h cross square. By rearranging it, we can write this equation that E is equal to h cross square alpha square upon 2m. After substituting the value of alpha square here and substituting the value or h cross as h upon 2 pi, it results in the equation E is equal to n square h square upon 8m a square, which is essentially the same expression for a particle in a rigid box, which means that particle can have a discrete energy levels corresponding for n is equal to 1, 2, like that, like a ladder of energy, but essentially a discrete energy levels. Now let us go to the other extreme. Let us say that P is tending to 0. Look at the equation, Kronig-Penney equation, which is written in the top. If P is tending to 0, this equation would be satisfied if alpha A would be equal to Ka. That means alpha is equal to K. And if you put it in the same expression for E, then you get h cross square K square upon 2m. Now, there is no restriction on the value of energy that particle or that energy that electron can have. E varies continuously with the K and all energies are allowed. Now let us think about an intermediate case between 0 and infinity, let us say. Then the conclusions which are drawn by the equation from this Kronig-Penney equation is it consists of allowed bands, certain band of energy which is allowed, which are separated by the forbidden gaps which electron cannot have, and width of these allowed bands increases as energy increases, and width of forbidden gap decreases. These are the conclusions that we draw from this Kronig-Penney equation. In this utility, whatever we have said or established through mathematics, we would see it exactly in that utility. So to summarize, what we have seen on the previous page is free electron can have any energy, no restriction on it. And suppose P is tending to infinity, that is called as a tight binding, and we got a discrete energy levels are allowed. If it is an intermediate case, then this blue band, let us call it as allowed energy band, and then there is a gap between the two bands which is a forbidden gap. And as you are able to see in this picture, that width of a allowed band is increasing as you go up, where the energy is along y direction, and the gap between the bands is getting less. Here it is more and here it is less than that. Now we will see it through the Excel utility. Let us have a look. Now friends, in this, what you need to change, let us have a look at it. Here P value, we can put whatever value we want to put here. Then there is a column alpha A just with some in small increments. Alpha A is a column there, and then from that sine alpha A upon alpha A is computed, cos alpha A is computed, and left hand side, that is P sine alpha A upon alpha A plus cos alpha A, which is a left hand side of a Kronig-Penney equation that has been computed. Now what we need to do is here we need to change the values of the P here, and then everything would change automatically and we can certainly judge from this particular graph. Now before we move ahead, friends, understand one thing, that left hand side should be between plus 1 and minus 1, that is of our interest, because right hand side is a cosine term and only those values of alpha a is allowed for which left hand side lies between plus 1 and minus 1. That is the idea about it. Now look at this graph. What is this graph? Left hand side is plotted as a function of alpha a. Do not look at the absolute values that you see on x-axis. It is normalized. Okay, now let me format this axis. This is, we are interested in between plus 1 and minus 1, but let us go stepwise. I would first put it between minus 5 and 5. Let us have a look at the graph. Then in the next step, let us make it minus 1 and 1. Now let me first change this value so that we can understand things better. I have just set the value of p and everything has been updated. Now friends, understand what values we were interested in, for which left hand side is between plus 1 and minus 1, and understand that graph is beyond this. Graph was something of this kind which is going beyond plus 1 and minus 1, but we were interested between these two values. Now look at the values of alpha a which are allowed. Now look at this. That means what is the width of alpha a? Let us, as I said, let us not look at the labels on x-axis. Let us look at roughly the width of alpha a which is allowed. Okay, and to guide our eyes, there is a grid lines over there to make some judgment out of it. Now you can see that change or a width of alpha a is roughly, for which this graph is lying between plus 1 and minus 1, is less than 1 square, right? From this point to roughly slightly beyond that, let us say it is less than 1. So these values of alpha a, this range of alpha a, this range of alpha a is allowed. So correspondingly alpha is allowed, correspondingly that particular energy band is allowed. Now look at this, from here it is going beyond minus 1. That means from this value to about this value, alpha is not allowed. That means this would result in a forbidden gap in an energy level diagram. Now look at the next point, that now next band may, how much is the width of alpha a. Now let us look at this point and this point, and you are able to understand that in the first band the width was less than 1 square, and here you can roughly judge it is more than or close to 1.5. Look here, it starts from this particular point and it goes up to this. So this is allowed. So it has the width of alpha a has increased. So width of alpha is increased. So width of allowed energy band has increased. Let us look at the third band, and you would understand from here in this graph that now width of alpha a which is allowed is slightly more than the two squares. You can see from this point to roughly about this point, that is amounts to two squares in this diagram. And if you look at the next one, you would see 1, 2, and close to 3. So that means width of the allowed band is increasing. That is number one, which we are able to draw the conclusion. And second conclusion, let us look at how much is a width which is not allowed, which is resulting into a width of a forbidden gap. Now here 1, 2, 3, little bit more, 3.5. Okay. Now this is the width which is not allowed. Now the next one which is not allowed is slightly less than 3. Now look at the next one. Here you can see it has become 2.5. So if you observe it clearly, then we would convincingly understand that because of the curvature of this p sine alpha a upon alpha a plus cos alpha a, and because of this nature, let me zoom it, then we are able to clearly understand one particular point, that width of the allowed band goes on increasing and the gap between them goes on decreasing. That is number one. Now, that why this happens? Because of the nature of this graph, whose amplitude is decreasing as value of alpha a is increasing. Okay. Now I would increase this value. Let us make it higher side. Let us go and let us try to understand that how does it becomes a discrete allowed energy levels. Now again, I would zoom it in a two steps between +1 and -1. First, I would zoom it between +5 and -5. Then let me in one more step, let me zoom between +1 and -1. And you would understand that lines, you can see that almost vertical. So what is a range of alpha? You cannot see the range of alpha which are allowed. Rather, you would understand that they are very steep. They are almost like a vertical lines which are parallel to axis, almost. Okay. So that means one particular value of alpha is allowed. That means one particular value of alpha is allowed. So it would result into a discrete energy levels which are allowed. So we are able to understand that if P is high tending to infinity, then it results into this kind of a picture, which is similar to a particle in a box. Now let us go to the other extreme now and let us try to see what happens in this case. Let me put it. Now what happens? Let me decrease it by one more decimal point. Now you see that all the graph for this particular value of P, left hand side is well within +1 and -1. That means all the values of alpha a are allowed, all the values of alpha are allowed. So that means all the energy levels are allowed. There is no similar to the other two cases, intermediate and this tight binding, is there is no such restriction. When P is tending to 0, it is becoming a free electron which can have any energy. So that's all about this particular utility, friends. In this, you need to change this particular number which is highlighted in a yellow color, and by changing it you can analyze everything through this graph and you would get this file just near to this video on the same page. For additional readings, you may refer Solid State Physics by Ashcroft and Mermin, Introduction to Solid State Physics by Charles Kittel, and Introduction to Solid State Physics by Yeso Pillai. If you have any doubt, if you want To ask me any queries, you may reach me at my email address. Thank you very much.